just like, what do you want to talk about?
All right. Good evening, everyone. You could also, for a quick second, take a break from your lively conversations. Hope that everyone's food and drinks are delicious. Thank you all for coming out tonight to Science on Tap for our May edition. And we have Anna Rosen tonight. My name is Monica, and I'm the Vice President of the Women in Science and Engineering at UCSC, which is a student-run organization that looks to foster the development and participation of women in the STEM fields. And one of our activities that we do is Science on Tap, and where we bring a local scientist or someone up on the hill to come and give a diluted presentation to a lay audience so that we can understand things like supernovas. So tonight we have Anna Rosen, and she gave me a little bit of her history. She started at a community college where she started studying physics and astrophysics, and then she transferred to UC Berkeley, where she got her bachelor's in science. And then she went to UC Santa Cruz, and where she was an NSF graduate research fellow. She also had an AAUW dissertation year fellowship, which is very prestigious. What does AAUW stand for?
American University, American Association of University Women.
Which is another reason why she, was the perfect WISE candidate for tonight. And she recently, in the past month, has gotten her PhD. So kudos to Anna. And she'll be leaving the West Coast for the East Coast, where she'll be beginning a NASA Einstein postdoctoral fellowship at Harvard in the fall. So another big kudos to Anna. So pretty amazing superstar that we have tonight to talk about supercomputers and stars. So I'll stop with the puns and let Anna give her presentation. Thank you guys again so much for coming tonight. And with that, I will let Anna take it away.
Great. Well, thanks guys, and thanks Monica. I was really excited when Monica asked me to do this. I've been involved with WISE since I began grad school. My old housemate was actually the president of WISE a few years ago. WISE is definitely one of those really great activities or organizations on campus. I've been involved with a lot of outreach and stuff like that with them. So, of course, when Monica asked me, I couldn't say no. So today I want to talk about, partly about my research, but I'm going to kind of go to astronomy from a different standpoint, what you guys might actually think when you think about astronomy. So what I'm going to talk about tonight is how to make massive stars in a supercomputer, and I'm going to talk to you guys about astronomy from a theoretical aspect and how we can use what we know about physics and astrophysics to simulate physical phenomena in the universe. And of course, since we're at a bar, I decided to create a drinking game. So feel free to join. And the rules are, whenever I say star, you have to drink. And that's the only rule, so have fun with that. And if any of you guys quit early, I won't judge you. But, try it out. So to just begin, I want to talk about, what is astronomy? We all kind of know. Astronomy is, the field of science where we want to study the celestial objects in the universe. We want to study planets, stars, and galaxies, and what, the physical meaning of our universe is. And why do we want to study astronomy? Well, there's several reasons why, and this is from the NASA website. So if you ever look at the NASA education website, there's three main questions. The first is, how does the universe work? How did the universe begin? How will it end? And what is it made of? What about the exotic things in our universe? Black holes, dark energy, and so on. What do those things mean, and how do they evolve with time? Also, how did we get here? How did our galaxy become what it is? How did the first stars evolve? And what will happen to our solar system in billions of years to come? And then finally, what everyone wants to know is, are we alone? Right now we're discovering thousands of exoplanets. Are we the only intelligent life in the universe, or could it be common? Are we special? Are we not that special? And what is the chemical makeup of these other planets in our universe? And the way that we do this from an astronomy standpoint is to look at light from distant objects. And the way that we do that is to use ground-based and space-based telescopes. And so what I'm showing here, this is also from NASA Wengo site. Can you guys hear me? Okay. And so we have a lot of space-based and ground-based telescopes. And these different telescopes measure different parts of the electromagnetic spectrum of different types of light. And so here I'm showing you electromagnetic spectrum. We go from high energy, like gamma rays, so these are high energy photons, all the way down to radio waves. And we have to build different types of instruments to be able to measure these different types of light. And then with that too, we also need to understand where this light comes from. And so the nice thing about knowing about what light we need to collect, about how to study these distant objects, we can study so many different things. And this is just kind of like, a brief overview where we can study how planets form. What do different planets look like? In our own solar system, we can take close-up pictures of planets from our own solar system, but we can also detect planets in other solar systems. We can study our own star in exquisite detail. But then we can also study how stars outside our solar system form. What kind of stars form? How big are they? And then what about stellar evolution? How do these stars evolve with time? And how does that depend on their initial properties or on their initial masses? And then finally, how do they die? How do they end their lives? And then also we can study them in clustered environments. Most stars form in clusters. And then those clusters mostly are in galaxies like our Milky Way galaxy, and also Andromeda, our closest neighbor. Sorry, there you go. There are the pretty pictures. Okay, so we can study how planets form. Okay, so this is just an example of all the things that we can study in our universe. I'll just go over it again since I didn't have it up. And so we study all things as small as planets and how planets form through around stars. So these are disks around stars that can coalesce to form rocks, big enough rocks that become planets eventually. We can also study how stars evolve and die, and also how they form in clustered environments. So they don't usually form in isolation. And then those star clusters actually belong to greater structures known as galaxies, like our own Milky Way galaxy. But we can also study the dynamics of galaxies too. So, these galaxies will interact through gravity and they can merge and so on. And then with telescopes like Hubble, we can look at in the past and also see young galaxies from billions of years ago. And finally, with other big range telescopes, we can study the structure of the universe. So this is the Sloan Digital Sky Survey, where we map out all the galaxies to give us an idea of how the universal structure formed over time. And another thing too is to try to understand the beginnings of the universe. So this is an example of the cosmic microwave background. So looking at microwaves, we can study how the light from the Big Bang looks to us today. And so this is just an overview of the fact that even with these ground-based and space-based telescopes, we can study so much about the physical properties of our universe. And then there's a lot more that's going on. It's a big place. And so there's one that, we can take pictures of this, but to really understand it, we need to understand the physics that govern these processes. And this leads us to astrophysics. So right now I think astronomy is turning more into an astrophysics focus. We can take the pretty pictures, but we want to understand, where does that light come from? Why do we get to observe that light? And what does it mean? And so astrophysics is basically, it's a branch of astronomy where you want to be able to apply the laws and theories of physics to the interpretation of astronomical observations. And so yes, we can take these pretty pictures, and with those pretty pictures, we want to be able to understand what they mean. Okay, so going into that, when we talk about me, so what do I study? Well, I study stars. I study how massive stars form and how their formation affects their environment, and I'll get more into that later. But before I go into talking about my research, what I really want to motivate is why are massive stars, so these are stars that are greater than 10 solar masses and above, why are they important, and why is their formation important? Like if they form, why does it matter? And then also, how can we study their formation in real time? So just to begin, I just want to give you a brief overview of how stars form. Stars form under the gravitational collapse of cold, dense, turbulent gas. And so this picture here is actually from a friend who finished her PhD in Europe. This is from the Muse instrument. It does images. It also does spectroscopy, meaning that it can see gas that's moving towards us and away from us. And being able to see how the gas moves towards us or away from us, we can actually get a 3D view of this. So this is a 3D image of a star forming region that we call the pillars of creation. And it's hard to kind of see the stars that are forming here because this is visible light. These regions are very dusty, and the dust is opaque to visible light. But if we take something like Hubble, the Hubble Space Telescope, and we look at it both through visible and infrared radiation, you see that when you look at it in the visible, you just see all the gas and dust. But you can look through that dust when you use infrared, when you look at the infrared light. And so you can see all these stars that are forming in these dense regions. Okay. So, regions like this, where you see these stars collapse, these gas clouds collapsing to form stars, you get a broad range of stellar masses. Stars like our sun, even lower mass, and more massive stars. And, we think we have an idea of what the mass distribution of stars should be. So if we look at all the stars in our galaxy and other nearby galaxies, we can measure what is the probability of getting a star of a given mass, just overall. And so this is known as the stellar initial mass function. It kind of says if I want to know the probability of getting a five solar mass star, I can describe it by this probability distribution function, which is motivated by observations. And if we look at massive stars alone, so let's say 10 solar masses and above, you find that about only 1% of stars are massive. However, these stars are very bright. So this is R136, which is a massive star cluster in the Large Magellanic Cloud, which is a star cluster, and the Large Magellanic Cloud is a satellite galaxy to the Milky Way. And you see these stars look very blue, and that's because they're very massive and very bright. And it turns out that these stars give off, they can give off 1 million times the amount of radiation than our sun. And so they're going to exhaust through their nuclear fuel very quickly, but they're going to feed a lot of radiation and energy and momentum from the radiation fields into their surroundings, so they can actually be quite destructive, much more destructive than our sun. And so if we take that into account, by number, massive stars are only 1% by number, but if we were to look at the energy output from those stars alone, you find out that for a newborn stellar population, about 97% of the radiation energy, it comes from the massive stars alone. And so they actually massive stars dominate the energy budgets of star-forming galaxies like the Milky Way and other star-forming galaxies. And so you can kind of think of it as massive stars are the 1% of the universe. And another way to see that is to look, so here's R136 again, and this is the region that it formed out of. There's all this gas and stuff, and it turns out that the amount of energy momentum that stars or star clusters like these output can actually be very destructive to their environment. And so this is known as stellar feedback. It's just how stars feed back on their environments from their radiation fields and other forms of energy, momentum input. And so this right here is a 30 horizon in the Large Magellanic Cloud. It's a giant star-forming region. R136, which is one of the most massive star clusters in our local universe, is right there. And you can this is a great image to kind of show how stars affect their environment. This is a composite image from data from Spitzer, which is an infrared telescope, also a ground-based telescope that measures visible light for the H alpha, and then the Chandra Space Observatory, which measures the X-rays from really hot gas. And to kind of put you through this picture to see how destructive these massive stars are to their environment, you see that first, you see this direct illumination from the stellar radiation fields themselves in the H alpha. And thus dust and gas will absorb energy momentum from the stellar radiation fields from the stars, and that will heat up the gas and dust. And then that dust will re-emit radiation, infrared wavelengths that we see here in the red by Spitzer. And so even though the stars are mostly here, they're going to affect adding energy momentum to the gas much farther out. And then finally, these stars also have, also because they have such high radiation fields, they can actually push atoms off their surface really quickly, and so you get these fast stellar winds that also can shock or collide with the gas and other winds, and that gives you really high temperature gas. It shock heats the gas to really high temperatures of millions of degrees Celsius, and then that gas will expand and also push on the cold gas. So what really happens is that these stars are putting so much energy and momentum into their environments that they're making it difficult for the gas to collapse to form more and more stars. And it turns out that stellar feedback is important on many scales. So just on the small scales alone, so if we look at individual star formations, so for massive stars, like I said, the radiation energy output is very important. It can push on the gas that could otherwise collapse into the stars as they form. We also get the stellar winds that can, again, push away the gas. We also have protostellar outflows that are launched from the poles of the star that can push gas that could fall along the poles of the star. And then finally, at the end of their lifetime, these stars will explode as supernovae and can just inject a lot of energy and push on the gas and making it difficult. So these forms of stellar feedback can actually halt accretion onto the stars and thereby limit their masses. Now on bigger scales, because most stars form on clusters, the integrated effect of feedback, so if you add up all the energy and momentum that these stars put into their environment, can actually push out a lot of the gas that would otherwise go into forming stars. And so here is NGC 3603. It's a star cluster in our galaxy. And you see that there's all this gas around it, and this gas was pushed out by the radiation and winds from these stars. And so it's heated up so that this gas will likely not form into stars. So this actually leads to low star formation efficiencies in molecular clouds, in which most of the gas is ejected before being turned into stars. And then finally, if you look at larger scales like galaxies, over the whole galaxy where you have these supernova explosions and radiation and so on, you can eject a lot of cold gas that way, and that can lead to low star formation in galaxies themselves. And one way to see this again is to look at the different multi-wavelength observations from different telescopes, combine them to get a better idea. So this is the same galaxy, this is M82. The red shows all this cool gas that's being pushed out of the galaxy from supernovae. And then when you combine the the higher energy radiation, so from X-rays, you see that it's really this hot gas that's generated by stellar winds and supernovae explosions that's pushing the gas out. Okay, so stellar feedback is destructive. It can lower star formation in galaxies and eject a lot of gas outside of galaxies. But why else are massive stars important? Well, it turns out if you look at the periodic table, if you want to understand where most of the elements in the universe come from, we really need to know how those elements are produced. And most of those elements are produced in the cores of massive stars because they're so big. They can fuse larger and larger elements. And so this kind of shows here, this is a plot from a friend, where he showed the relative abundances of all these, different elements on the periodic table. And even though, compared to hydrogen and helium, heavier elements are tiny, the amount is tiny compared to that, to hydrogen and helium, most of these elements are made in massive stars. And so for life to actually happen, for us to have the chemical makeup that we need, you need nuclear fusion from massive stars. And then also elements larger, so if we look at supernovae, so elements that are typically larger than iron are actually produced in supernovae explosions. And so here's just a picture of the remnant of a supernova explosion from a massive star. And so as these explosions expand into the galaxy, they can mix heavier elements, and then future generations of stars can have more and more heavier elements in them. So you can think of that the formation of massive stars has important consequences for both galaxy evolution and the chemical enrichment of the universe. Okay. So hopefully you guys all think they're important. Now, one of the problems is that studying their formation is actually very difficult because their formation timescale is very quick. They form in these dense regions that's really hard to probe against. Not only that, like I said, massive stars are rare, which means that the sites where they form is also very rare. So observing them is much more difficult than low mass star formation, for example, is less common. And being able to study their formation in real time and also in detail can be really challenging because of these limitations. And not only that, so this is the Carina Nebula, this is a Hubble image. You can also do a close-up there where you see that you have these massive stars, causing gas to dissipate away near the stars, but also push gas up against it, so you even get these more opaque regions to be able to look through. And so studying their formation up close is very difficult. However, as it turns out, and like I showed before, if you look at longer wavelength observations, so instead of looking at the visible light, if you look at the infrared and the microwave, we can see stuff into more detail. And so space telescopes like Herschel, which can look at cold gas, because microwave observations, you can see these sites of massive star formation. And so if you look at the blue here, you see these traces the energy input by massive stars. The radiation fields of these stars hit the gas, and so we'll see the gas emission at shorter wavelengths, higher energy. And so you can see these sites of massive star formation, but it's still highly obscured. Here's another image from Herschel, and you'll see that basically the most massive stars tend to form the densest region, so along these dense filaments where gas could be funneled to the stars. So, we have a good idea. We know that these stars form in massive and dense regions, and that the radiation energy input can actually affect their formation, but it's hard with observations alone to study how the energy input by these stars affect their formation. And so if we really want to study their full formation in exquisite detail, how can we do that? And one way to do that is to actually do numerical simulation. So this is us trying to simulate physical phenomena in real time on giant computers. And we use this for, variety, for all fields really. And the basic concept is that we want to be able to solve the laws of physics in a on a computer to solve research problems. And to do this, we have to use a variety of programming languages. We need to know C++ and Python and Fortran, etc. But we also need to know parallel programming languages so that we can run these simulations on lots of processors, because these simulations are very big to run. And like I said, these simulations are very big to run. And so we have to run them on hundreds of thousands of computing cores. And so we use we use supercomputers at national labs, like at NASA Ames or NSF and so on. And so, for example, the supercomputer at NASA Ames, which is just over the hill, contains over 200,000 CPUs, has a lot of memory, And it's this giant room just dedicated for scientists to sign on and do computational simulations. And okay, sorry, this is the one slide with equations, but I'm only added this to prove a point. You don't have to know calculus to do this. But the way that we solve these simulations, like I said, we want to solve the laws of physics on a computer, and we want to be able to evolve these systems in space and in time. And so what we're doing is we're solving the laws of physics on a 3D grid, and we're using the definition of derivatives. So if you go back to calculus, where you're, instead of solving a differential equation exactly, you're discretizing it. So you're using the fact that you have these cells and you can evolve these equations in space and time. And that's all we're doing. And so, for example, these equations here are what we use to evolve astrophysical systems. These are known as the fluid equations. They're used in monitoring weather, civil engineering, all those things, anything that you can treat as a fluid. And they just basically talk about mass conservation, so you can't lose mass. Also force conservation, so the momentum equation describes momentum conservation, which is Newton's second law, force equals mass times acceleration. And then the energy conservation. So that just means that you can't add or lose energy, you have to conserve energy. And then as computational astrophysicists, we have to know what physics are important to include for the physical problem that we're solving. And so that's just because any additional physics that we include will make these simulations more expensive. So we have to be clever about what we want to include. And the results that we'll get are highly sensitive to the physics that are used. Okay. So what are the challenges in star formation simulations, and how can we get over those challenges? So the first is that there's a large dynamic range. We're going from the size scales of galaxies down to the size scales of molecular clouds, so light year size scales, down to the size scales of stars. So like our sun is 10 to the 10 centimeters in radius, but we're going down from light year size scales that are like 8 orders of magnitude larger. So we need to figure out how to cut the dynamic range. We're also going from lowish density environments all the way down to the densities of stars themselves. Also, massive stars are very luminous, and so you really have to model the radiation pressure associated with their formation. So you have to properly model radiation from these stars. Like I said, they can maintain their full luminosities while they are still forming, and that can have drastic implications for their environment. And if you want to fully model how the radiation will couple to the infalling material, you want to solve what's known as the radiative transfer equation, but that's a very complicated equation to solve. You have 7 dimensions. You have 3 spatial dimensions, x, y, and z, but you also have angles, time, and also a frequency dimension, or a wavelength dimension. And then also, the more difficult the problem is, the longer it takes to solve. And so if you want to, for example, for me, I of course wanted to finish my simulations during my PhD, and so you have to compromise. And so one thing that we do, and I'll talk about next, is to use this technique called adaptive mesh refinement, in which you basically just refine, so get better and better resolutions on the regions that you care about, just to look at the regions that you care about and ignore the low density regions that you don't expect stars to form. And instead of resolving individual stars, we have particles that can act as stars that also have a protostellar model attached to them to model the radiation fields. And then instead of modeling radiation from these stars exactly, we just do approximate radiation scans. And I'm going to that now. Okay, so adaptive mesh refinement. So the way that this works is, like I said, so before, we model everything on a 3D grid. So here what we do is we have everything as a 3D grid, but then we only want to focus on the areas that we care about. So the areas that we expect stars to form, so the higher density areas. So we have our level 0 grid, which is the lowest resolution, and then we add our level 1 grid. And so that gives us a factor 2 refinement better. And then we go again to higher density regions, and we do better refinement. And then finally, if we're on our finest level, we're going to add stars in the coldest, densest region. And so we want to do this on the fly. So that means every time we evolve our equations, we want to look and see, okay, do we need to refine on these areas? And so here's an example of on-the-go refinement with time, in which you have a shock just going through the box, and you'll see that you refine on the criteria chosen by the user, and so this could be velocities or densities and so on. And so for this specific example, they decided to refine on the velocity, and so you'll see a shock will go through the box, but that shock is going to be very nicely refined throughout. And so this is how adaptive mesh refinement progresses through a simulation. Show that one more time. So this is something that you have to constantly check as you run your simulation. So this saves a lot of cost because you have low resolution in areas you don't care about, so you're not spending a lot of time on that, and you just resolve the areas that you do care about. Another thing too I said is that you want to be able to pick the physics that you have to include. You can't include everything, and so you have to be clever about that. And so for massive star formation, we have to make sure to include radiation from the stars. And there's two components to this, as I showed in this image earlier. We first have the first absorption of the radiation, of the stellar radiation by the surrounding dust and gas, but then that dust and gas will heat up and re-emit. And so you get this re-emitted dust or process radiation. And so there's two radiation fields that we want to model. And so a lot of my PhD was to try to study how radiation pressure could affect the formation of these stars. Because if you just do simple analytical arguments, so not these 3D simulations, what you find is that if you just had simple like isotropic accretion or spherical accretion onto these stars, you would expect radiation pressure to be strong enough to blow the material away when the star is about 20 times the mass of the sun. And we observe stars much greater than this, and so that means that something else must be happening. And so a lot of my PhD was to treat the radiation fields better in these simulations. And so, for example, to model the stellar radiation field, we do ray tracing from the stars. So we basically just shoot rays from the star, and each ray has a luminosity based on the star's properties. And then as these rays go through the gas and dust, you can solve the radiative transfer equation exactly along these rays, and then add the energy and momentum to the gas and dust. Exactly. And so that just kind of shows you here where you have a dense cloud illuminated by two stars. And of course, the radiation will get absorbed close to the surface of that cloud because it's very dense, and you get this nice shading there. It's just like, shadows in real life. And like I said before, so you have the absorption by the stellar radiation, but then the dusty gas will also emit radiation. And so we have a different method to treat that, where the radiation is all throughout the domain, and then you just add them together. And so we developed this hybrid radiative transfer method to be used for numerical simulation. And it models the radiative heat and pressure from the stellar and the dust or process radiation field. And so with that, we added it to an AMR code, and we can simulate the formation of massive stars based on our observations of how these massive stars form. And so I'm going to show you the simulation of a massive stellar system out of a 150 solar mass cloud. So this cloud has a mass 150 times that of the sun. And the core size is the radius is a fraction of a parsec across, in agreement with observations. And what I'm showing up top is the full core collapsing, and on the bottom is a zoom in. Here I'm showing one direction, so this is the YZ plane, and here is the XY plane. You see a disk form around the star. And so I will just play that now, and we start with the turbulent initial conditions, so the gas itself is going to be turbulent. and that will affect how gas is delivered to the star. And so you see, as the star forms, the radiation pressure is pushing the gas away from the star, but you get these dense filaments that are uninhibited by the radiation pressure that can fall into the star still, whereas the low density regions are pushed away. And so one way to get through the problem of how do you form a star bigger than 20 solar masses is that you just have to have this anisotropic accretion flow dumping material into the star through these dense filaments. And you also get a little accretion disk at the end. I'll show that one more time. So the radiation tries to push the gas away, but the dense filaments can actually fall towards the star cell. Because gravity is much stronger for those dense filaments. And at the end here, we get a star that's over 60 solar masses. So 60 times the mass of our sun. And so basically what we're finding is that, the mass is delivered to the star, through these infalling dense filaments. And radiation pressure carves out holes like in the low density regions around the star. And then you also get an accretion disk around the star that can also deliver material to the star. And so here you can see radiation blowing material away from the star, but you get these dense filaments delivering material to the star. And then likewise, towards the end, you see that we get this nice accretion disk around the star that is also delivering material because it is high density. So, did I solve all of mass star formation? And the answer is no. So we focused the concept of massive star formation just looking into radiation pressure, because that was always what people thought was the biggest inhibitor for delivering mass to the star. But like I said before, there's, as we do these simulations, we have to pick and decide what physics to include to see how, those different, how that physics can actually affect the formation of these systems. And so to really understand if stellar feedback can affect the upper mass limit of the stellar initial mass function, is we need to include these other physics. We also need to include magnetic fields too, because it turns out that the gas that these stars form out of are magnetized. And that can also act as an anti-gravity. Okay, so based on the world now, I really wanted to include this, because I've had people ask me, like, how do I get paid? And so the question is, how is astronomy funded? Do you guys know? No, exactly. No, you're an astronomer, you can't say. Yeah, well, you're a scientist too, you can't say. So how is astronomy funded? Yes, so the NSF, so the National Science Foundation, and NASA are in charge for most of the money that goes into astronomy. So this is for NASA, for example. The reason why the budget is so much higher for NASA is because they're in charge of all the space-based telescopes and so on. They're also building the next big telescope, the James Webb Space Telescope. So what I decided to do to kind of illustrate how much money goes into it and how much we all pay for it. So looking at the 2015 numbers, it turns out that about 1.28 billion went to NASA, and 250 million went to the NSF. But to put it into a better context, I decided to put it in units of defense spending. So in 2015, about 600 billion was spent on defense spending. So the amount that we're paying on astronomy and other fields similarly is a fraction of a percent of our budget. And then you can do the math. Well, if about 120 million people pay taxes per year, how much are each of us paying? And it turns out that in total, it's about $1 per month per person. And so, based on your contribution of $1 per month per person, what have we figured out? What have we discovered? Well, since 1995, and using telescope or space-based telescopes like Kepler, we have discovered nearly 3,000 exoplanets outside our solar system. And for context, for comparison, I put the planets within our solar system on here. And it turns out that these exoplanets in the external solar systems are different from ours. And so this is providing a lot of insight, like, are we special? Maybe. And Another thing, like I showed before, is, for us trying to understand where the universe came from, we were able to measure the cosmic microwave background, which is a light relic of the Big Bang. So this is light that was emitted 380,000 years after the Big Bang. And I really like this image here because it shows how much technology has helped us. Within 30 years, how better we can look at this. So Kobe was the first mission that measured this, measured the light, the cosmic microwave background. And now, a few years ago, we have the Planck telescope, and you can see how much better the resolution has became in only 30 years. Also, Kobe won the Nobel Prize in 2006. Another thing that we've learned within the last 20 years or so is the fact, the universe is expanding, but it turns out the expansion of the universe is accelerating, which means that it's going to expand forever. And one way, this is another Nobel Prize that was awarded in 2011, and what they did was they looked at supernovae, so these type 1A supernovae that act as standard candles. They should have the same brightness regardless of where they explode. And they look at these types of explosions in a number of galaxies, and by looking at the fact that they didn't act as these standard candles, that their brightness dimmed the farther away they were, taught us, or we discovered that the expansion of the universe is accelerating. And then just recently, hopefully you guys all heard this, LIGO just discovered gravitational waves, which validates Einstein's theory of general relativity. So just to illustrate that here, they discovered the merging of two black holes that were originally massive stars. And because space-time wiggles due to the movement of massive bodies, you get these gravitational waves. And then once the system merge, these two black holes merge, you kind of get an increase in gravitational waves that can travel to Earth. And so this happened when in a galaxy 1.3 billion light years away. So we watched the merging of two black holes that happened 1.3 billion years ago. And then if you're interested in learning more about gravitational waves, there's going to be a talk at the Rio Theater tomorrow night about this discovery. So go there, 7 p.m. And then where a lot of the money is going now, so we all know about Hubble, where the next big telescope is the James Webb Space Telescope. It's going to be bigger, it's going to have a bigger wavelength range, it's going to be able to look at earlier epochs of the universe. So we can look at how the first stars form, what do baby galaxies look like, we can look much farther back in time. They can even potentially directly image planets, exoplanets. And so this will be coming out. This will be launched in 2018, so keep your eyes out. There'll be lots of pretty pictures from that. And so, thank you.
Yes, we have time for questions.
Yeah. That's the simulation in full.